check which applications are created under our current context. So I'll go ahead and write fn list apps and hit enter. As you can see, there's only one application which is currently created under the compartment function underscore demo called hello world hyphen app. Now with this, we complete our step 3. Moving on to the step number 4. As part of step 4, we will be creating our first function. We will deploy it to the OCI functions, and then we will invoke our function. So let's again switch back to the OCI console. All right, so in order to create our first hello world Java function, we'll have to use the fn init command. The fn init runtime java hello-java command, what it does is it creates a directory called hello-java and creates several files under it. So let's go ahead and hit enter. As you can see, it's created a hello-java directory which contains the function boilerplate as well as a function.yaml file which contains the function's definition. Let me quickly do an ls. As you can see, we have this directory created. Let me move into this directory and do an ls to show you the contents. All right, so as you can see, we have a function.yaml file which contains the function's definition. We have an src directory which contains the Java code, and we also have a Maven configuration file called pom.xml that specifies the dependencies required to compile the function. All right, now that we have created our first hello world Java function, we need to deploy it. In order to deploy this function, we'll have to use the fn deploy command, and also make sure that you must be inside the hello-java directory in order to run this command. So fn-v deploy -app and the application name which is hello world-app. Let me hit enter. And as you can see, what this command does is it builds the function and its dependencies as a Docker image called hello-java, and it pushes the image to the specified Docker registry. And it will also deploy the function to the Oracle functions in the hello world-app application which we created earlier. Now, just to show you that the image that we created is loaded into an OCI registry, let's quickly go to the OCI registry and see if we have an image called hello-java with a tag 0.0.2 available in the OCI registry. So to go to the OCI registry, first I'll minimize this Cloud Shell, click on the hamburger menu, go to the developer service, and click on the container registry. Now, within the container registry, let's select the root compartment. And as you can see, within this repository, we have this image called hello-java with the tag 0.0.2. So let's go back to the Cloud Shell. Let me quickly clear the screen. Now that we have deployed our function, it's time for us to invoke the first function that we just created. In order to invoke your function, you can use the fn invoke command followed by the application name and the function name. Let me go ahead and hit enter. For the first time, the fn invoke command will take some time for the function to load. Right? There you go. We have the output of the function as hello world. Now, if I rerun this command again, it won't take as much time as it took earlier in order to invoke the function. Right? So this time the result was pretty quick. Now we can also invoke the function with parameter. For example, if I run this command, it will pass Mahindra Mehra as a parameter to the function hello-java. Let's quickly run this command. And as you can see, the output of the command is hello Mahindra Mehra. Right? So with this, we come to the end of this demo on functions quick start on Cloud Shell. I hope you like this demo. Thanks for watching. Hello and welcome to this demo on creating a function from a custom Docker file. In this demo, you will create and deploy your code to the OCI functions as a custom Docker container using a node-based image. You typically use a custom image when your functions require a specific language version or have a specific dependency or configuration that isn't provided by the built-in image. Sometimes you also need to handle advanced use cases and must take complete control of the creation of your function container image. So let's build a simple custom function container image to become familiar with the key elements of the process. Let's get started. All right, so I've logged in to the OCI console, and the first thing that I'll be doing is creating a function application. Right, so let's go to the developer service, go to the functions. Under applications, I'll be creating an application where we will be deploying our custom function. So let's click on create application. But make sure that you are in the right compartment. In our case, the compartment that I have pre-created is functions underscore demo, where I'll be creating all my function resources. So let's select functions underscore demo and click on create application. Let's give our application a suitable name. So I've given it a name custom underscore demo. Let me go ahead and select the subnet. Let's select the public subnet and let's click on create. Okay, so as you can see, the application has been created with the name custom underscore demo, and we get to see a few getting started tips to begin with creating functions and deploying those functions within these applications. I'll be using Cloud Shell for the rest of the setup. So let me quickly launch the Cloud Shell by clicking on the launch Cloud Shell button. This will take some time before the Cloud Shell machine is created and we get the access of the shell. All right, so I have the access of my Cloud Shell now. Let me quickly maximize this Cloud Shell. So in the interest of time, I've already created a folder structure where I have all the required files in place. Let me quickly show you the folder. So custom underscore node.js is my folder where I have all the files. Let me get inside this directory. Let me show you the contents. All right, so as you can see, there are a few files within this directory. Let me quickly explain you each of them. So this is a node.js project. Let me quickly open up the function definition. Now if you see from the code, so what this function does is it takes a binary image as its argument and writes it to a temporary file, and then uses the ImageMagick software to obtain the width and the height of the image. Now, since the function argument type is binary, we need to set the input mode property to buffer when we call the FDK's handle function. So this is our function definition. Let me close this. Now let me show you the package.json file. Basically, this file contains all the Node.js dependencies. As you can see from the code, we have specified the list of dependencies that are required for successful run of this particular project. The dependencies include fn project FDK, a temporary module which is basically for your temporary file utilities, and again ImageMagick software that would be used to determine the height and the width of the image. Let me close this file and move on to the next file. So the next file that I'll be showing you is function.yaml file. Basically, this file contains the function metadata. Let me open the file. Right, so as you can see from the code, this basically contains the function metadata. Basically, the schema version, the name of the function, the version, the runtime. Now, if you notice, the runtime is not Node over here. This ideally must be Node as it's a Node project. Since we are using a custom Docker file to create a custom Docker image for this project, we have changed the runtime to Docker. Now, with that, since we have changed the runtime to Docker, we will also be needing a custom Docker file. So let me quickly close this file and show you the custom Docker file that we have written. Now, this is a custom Docker file that we have written. I have purposely commented this line just to tell you that if we do not use a custom Docker file, the fn build would normally generate this particular Docker file in order to build a Node.js function container image. But since we are doing a custom Docker file and we know that we want to have ImageMagick installed in our base image, now since we are doing a custom Docker file, we have this liberty to add libraries and new softwares within our image. Right. So what I'll be doing is I'll be uncommenting this line And what this will do is it will run the ImageMagick software in the FN project node runtime image. With that, we'll be able to make use of ImageMagick libraries. All right, so let me close this file. And as you can see, we also have a few sample JPEG images which we'll be using to invoke our function. Now, as part of the next step, what I'll be using the fn list context command. As you can see, there are two contexts. One is the default and one is my region, which is AP-Mumbai-1. And currently the context selected is my current region. So I'll leave it to that. The next thing that I need to do is to configure the FN project context with the OCID of the current compartment which will own the deployed function. So let's fire the command fn update context oracle.compartment-id and specify the compartment ID where my FN project resources are being built. All right, so the command is fn update context oracle.compartment-id and the compartment ID where you use to create your FN resources. Let's hit enter, and the current context has been updated. So the next thing that we need to configure is fn project context with the OCIR, that is Oracle Cloud Infrastructure Registry address in the current region and tenancy that we want to use with Oracle functions. All right, so the command is fn update context registry followed by the registry address. Right, so let me quickly go ahead and hit enter, and the context has been updated for registry. Remember, the registry address is basically the combination of your registry key .ocir.io / separated by your tenancy namespace, and then you have to provide a repository name prefix. In my case, the repository name prefix is MyMera. Okay, so let me clear the screen, and now as part of the next step, I'll be logging into OCI container registry, and the command for which is docker login -u. You specify your username and the registry address. All right, so I'll go ahead and hit enter, and in the form of password, you'll have to provide your authentication token. So let me go ahead and hit enter. All right, so as you can see, I've successfully logged in into the OCI container registry. Okay, so now that I have configured the FNCLI context and have logged in into the OCI container registry, the next step would be to build and deploy the function. So like I said, we have our custom Docker file ready. I'll quickly show you the list of files again. We can simply run the fn build command to build a custom container image for our function. The command is fn space -v space build. Let me go ahead and hit enter. So as you can see from the command, it is using the custom Docker file that we provided in order to create a custom Docker image, right? As you can see, it's using the two-stage build process in order to create our custom Docker file. As you can see, as part of step 6, it's also installing the ImageMagick software in our custom image, which is basically a runtime image, right, for the node project. All right, as you can see, at the end, we have our image built, and the tag that's given to that image is 0.0.3. All right, so now that the custom image has been built, the next step is to deploy this function into the application that we created earlier. Let me clear the screen. To deploy our function, the command is fn-v deploy-app and the name of the application that we created earlier, which is custom_demo. Let's go ahead and hit enter. As you can see, as the output of the deploy process, the custom image that we created is pushed into the OCIR, that is the OCI container registry, right? And the push operation has completed successfully. We can simply go to the OCIR repository and see whether this image exists. So let me minimize this Cloud Shell and take you to the OCI registry, which is available under developer services under container registry. All right, so the compartment is our root compartment. And if you see, we have this new repository created with the name image dims. And if I open this, you can see the image available under this repository. All right, so now that we have our custom function image created, it's time to invoke this particular function. I'll also take you to the function application and show you that the function has been deployed within the application. So let's go to the function service under developer service. Let's select the compartment, which is function_demo. And if we select the custom_demo application, you can see that there is a function is already created under the custom_demo application with the name image dims. And it also has information like if you wish to invoke it using an endpoint, or what is the image digest in order to check for the integrity of the image, etc. All right, so now let's go back to the Cloud Shell and invoke this function using CLI. Let me clear the screen. Now, in order to invoke this function, like I said, this is a custom function which takes as an input an image and returns the image's width and height. So we'll have to provide an image as an input. In our case, we have two sample images. One is image.jpg and another one is website.jpg. Both are of different dimensions. So let's quickly run each of them by this function and see what output we get to see. All right, so the command that I'm using to invoke this function image_dims, which is image dimensions, is basically cat image.jpg, where I'll be passing this image as an input to our application, which is custom_demo, which is hosting our function image_dims. All right, so if I hit enter, all right, so the output is the width and height. The width of the image is 553 and the height is 415. Now, if I rerun the command again, it won't take as much time as it took earlier. Now let's run the same command with another image as input parameter. As you can see, the width and height returned for the new image is different as compared to the earlier one. With this, we were able to create, deploy, and invoke an Oracle function using a custom Docker file. I hope you liked the demo. Thanks for watching.
Welcome to this course on API management. This is a level 100 course. My name is Robert Wunderlich. I'm a product manager with Oracle Cloud Infrastructure. In this course, we will discuss APIs and API Gateway. We will walk through the steps to prepare a tenancy for API Gateway, and we'll create some APIs. We will explore how we can use API Gateway to create a protected HTTPS endpoint for APIs, and how the gateway can apply policies that validate API requests, enforce authorization, work with runtime context, and transform API requests between our clients and our backend implementations. We will finish up with monitoring and managing APIs through logging and metrics. Let's get started. So what is an API and API Gateway? The term API, or Application Programming Interface, has been around for a very long time. Developers use them in many of the popular programming languages such as Java. Rather than implement everything from scratch, developers make use of libraries to accelerate their development simply by importing the libraries that they need. The developer interacts with the pre-built capabilities via a well-defined API. We can refer to this as a local execution because the developer imports the necessary libraries into her project, but it is encapsulated as the developer does not need to deal with the internal implementation of the API. Web services share the fundamental principles of encapsulating the implementation, but have some distinct differences. Like their name indicates, they are typically available over the web. They are highly decoupled, meaning that a client application invokes the web service over the wire. And the code for the web service does not typically run in the same context as the application that is using it. As a matter of fact, the web service is often written in a wholly different language than the client that is using it. As we've come to refer to web services as APIs, throughout this course, whenever we say API, we are talking about web services. So as we were talking about, what is the API? We have clients, and those clients need to use functionality on a server. So they connect to the server over the wire for the web service, which is a well-defined contract that we'll talk about in a moment. We need to be able to protect that endpoint because if that web service is available to the World Wide Web, anybody, not just the client we intend, could try to get to it. So we use an API gateway, and that API gateway provides an interface for the clients to be able to use and connects to the backend web services. So the client is not aware of the implementation of the backend web service. The client just interacts with the API gateway. So let's delve into the elements of an API. An API comprises a description, a set of policies, and an implementation. So beginning with the description is a contract between the consumer and the provider. It describes the functionality of the API. And there's a wide range of tools available for creating API description. You can use Postman, Stoplight, Swagger Editor, Code Editor, and many more. Description is typically written in a format such as OpenAPI, which is an implementation agnostic way to describe the behavior, and it's well recognized in the industry. When our API is being made available, that endpoint needs to be protected. And so we use the API gateway. The API gateway applies policies to enforce protection, such as authorization. It also performs validation, transformation, and routing. Another benefit of using an API gateway is it can add metrics, alarms, and logging for that endpoint. When implementing the actual functionality of the API, the choices are endless. You can implement on Oracle Kubernetes Engine. You can use Helidon. You could have custom code running on compute. You could create modern serverless APIs using Oracle functions. You could work against the Autonomous Database and Oracle REST Data Services. You can work against a wide range of SaaS applications. You can connect to just about anything with integration, or you can use any other technology. So the API gateway is a network-attached device, and it connects between the client and the backend servers. So the clients from the outside connect through the gateway to the backend services. And of course, those services can be running in OCI or through OCI connected to your data center. The API gateway provides security, mediation, and monitoring. So the Oracle Cloud Infrastructure API gateway is a serverless policy enforcement point. It adds authorization, rate limiting, and routing. It performs request validation. It also performs request and response transformation. To help ease the load on your backend services, it includes response caching. You can create both public and private endpoints. So you can have internal APIs running that are not accessible to the internet, and you can also have public APIs. You can also set up custom domains so that you can have APIs under your own host names. The gateway also includes integrated logging and metrics, and you can also use advanced logging analytics with API gateway. As you're designing your APIs in OpenAPI 2 and 3, you can load those into the gateway, and you can quickly create API deployments that have built-in mock testing. As you deploy your APIs and make those available for developers to create applications and use them, you can generate SDKs so the developers can work with your APIs in the language of their choice. Let's set up our tenancy for using API gateway. API gateway is a network-attached device. So if we do not yet have a virtual network, we need to first create one. The virtual cloud network, or VCN, contains multiple resources. For example, subnets. Our subnets can be both public and private. API gateway appears as a network device on the subnet of your choosing. API gateway is fully managed by Oracle, and it has built-in failover capabilities. Therefore, when creating a gateway, you will always use a regional subnet. When you create a gateway, the API gateway service automatically provisions your gateway with an active and failover instance. In a region with multiple availability domains, the instances are created in separate availability domains. If there is ever an interruption to the service in the availability domain the active instance is running in, the service will automatically fail over to the backup domain. In the case of a single AD region, the gateway will be provisioned across 2 fault domains. All of this is transparent to the user. As you set up your network, you will need to ensure that the traffic can ingress into and egress from the gateway. Oracle Cloud Infrastructure is secure by design and follows the principle of least privilege. This means that the appropriate ingress rules need to be added to the security list, and depending on your chosen network topology, you may need to add appropriate routes to your route tables. Continuing the principle of least privilege, access is never assumed, and policies have to be added to explicitly allow access. It is best practice to set up a well-defined groups in OCI identity management and then add the appropriate policies for the access needed. Users are not directly granted access to resources. Rather, policies are created to grant access to groups, and users are then added to those groups. When a new user is created, that user has no resource access until that user is assigned to a group. When enabling your teams to develop APIs, they will need to be granted the appropriate permissions through group membership. Resource-to-resource access is also controlled through policies. For example, if you want to create a serverless API with API gateway and functions, you must add a policy to allow API gateway to invoke the functions. Here we are in the OCI console. As we talked about before, we need to set up the network and also security policies before we use our first API gateway. Okay, so the first thing we want to do is go ahead and create a network. So I'll go ahead and go into networking, and I will select virtual cloud networks. Super important is to make sure that you have the appropriate compartment. Here I have L100 development checked, and that's what I want. So I'm going to go ahead and create a virtual cloud network. Now what I can do is I can create a VCN, or I can start the VCN wizard. So here I'll give my VCN a name. Again, I'm ensuring that I am in the appropriate development compartment, L100 development. My CIDR blocks are automatically filled out for me. I'll go ahead and leave those as is. And everything looks good, so I'm going to go ahead and create my VCN. The wizard will go through and create all of the necessary resources for my VCN. It's fairly quick. Okay, so my new VCN is created. Let's go ahead and do it. In my VCN, I have a number of resources. I have a private subnet and a public subnet. API gateway can work on either private or public subnets for different use cases. I also have a number of other resources created, such as my NAT gateway, my service gateway, DHCP options, my security list. As a matter of fact, security lists are super important, and this is something that will trip a new user up for API gateway. The example is I go in and create my VCN, and then I'll ultimately create my gateway, create an API, and I'll want to test it. And as I go to invoke it from my test client, from the internet, I will be confused in that I won't be able to get a response. My gateway will appear to me that it is not working. And what it is the security list has not been properly configured. So in this case, what I'm going to do is I'm going to go to my default security list for the L100 API management VCN, and I'm going to add an ingress rule. You notice here there's a default ingress rule of port 22, which is SSH. And that's all you get when you set up a network. OCI is secure by design. So there's no assumptions made as to what type of resources you're going to run. And all of your security lists are totally locked down, and you have to actively open up the appropriate ports. So I'm going to add an ingress rule. So what I'm going to do is I'm going to say 0.0.0.0/0, essentially everything from the internet. The IP protocol is TCP, and I'm just going to say 443. API gateway only allows HTTPS traffic in at this point. So what I'll say is HTTPS traffic for API gateway. This is an optional description, but just as I go back and I'm looking at this at a later point, and if I'm wondering why I have that open, I have a description telling you why. So super important step. Like I said, a lot of people, what happens is they get into trying things out, spin up the gateway, wondering why they can't connect to it. Simple thing, we just need to go ahead and allow, open the gate, so to speak, to allow that traffic to come into API gateway. So as far as networking is concerned, we're all set. Let's go ahead and create some policies. So I'm going to go to identity and security, and I'm going to select policies. Here, I'll create the policy. I'll give my policy a name. Allow API gateway, call functions. This is my development compartment. I'm going to go ahead and select the manual editor. This is a little more complex policy, but once we go through it, it'll make sense. So I have this already copied just for time, and I'll go ahead and paste this in. All right, so what does this tell us? We're going to allow any user to use functions family in the compartment development where, and these are conditions, all, the request principal type is API gateway, and the request resource compartment ID is this compartment ID. This is my development compartment ID. My gateway will happen to be in the same compartment as my functions, but I could have those in separate. So I could have a policy that is defining for functions in a separate compartment altogether. Different users are working on those, and I need to allow the gateway to be able to invoke those functions at runtime. This is for creating serverless APIs, and so we want to give API gateway the resource principal access to be able to invoke functions. So that policy is created. I could add a few more policies, and I'm going to go into another compartment just to show those examples. So if I look in this compartment, I have a set of policies for my API developers. I've set up a number of groups. I have API developers, API managers, gateway managers, and so forth. So my API developers can manage the API gateway. They can manage the network, the functions, everything within the development compartment, rather. They can work. They're free to do what they need to do to build their APIs. Just for context, a little bit of an example, let's go ahead and take a look at the QA compartment. So here I have access control for developers and testers for QA, UAT. When I take a look at this, I can see that I have a group API testers, and they can manage the API gateway in the QA compartment. Functions family, they can work with that. And if we look down the line, we can see developers can view those resources, but they can't change the resources. And that's as the API progresses through the development lifecycle. We do not want developers making changes directly in QA. We would want to limit that. So we have a testers group. And this is how we give rights to users to be able to work at development time and configuration time. We add those users to groups. So we assign the rights to the groups, and then we go ahead and create the appropriate policies to allow the appropriate access. But again, at runtime, that policy I created for the gateway is a dynamic policy of sorts, because any gateway I create in that compartment would have access. So I can add and change and take away gateways. I don't have to add each one into a specific group to solve that. So that covers what we need for networking and also policies. Let's go ahead and go create a gateway. So I'm going to go back to my menu. I'm going to select developer services. And under API management, I'm going to select gateways. I'm going to ensure that I'm in the correct compartment. So I'm going to select L100 in development. And I'll go ahead and create a gateway. Give my gateway a name. This one, I'll make a public gateway. You can make a public or a private gateway. And this one I'll make public because I want to have a publicly accessible address so I can create APIs and test against it. It's in the correct compartment, L100 development. I'm going to go ahead and select my VCN that I created, which is my L100 API management. And you notice we have regional subnets here, private and public. I'm going to go ahead and select public. Then I'll go ahead and create my gateway. Okay, my gateway has now been created, and I'm ready to go to start creating APIs and deploying them. In this module, we're going to create an API. We're going to begin with an API description, and we'll load that into API Gateway, and then we'll use that description to create a mock deployment. But before we do that, let's go ahead and talk about what this entails. Key element of creating an API is to be able to prototype that API. But we can create a description of the API. Ultimately, we're going to implement that API by creating a web service. However, that web service may not immediately be available after we've designed our API. Oftentimes, a team has to come and implement that web service on the back end in parallel with the team that's using the API on the front end. So what we can do is use the API Gateway. By loading our description into API Gateway, we can very quickly create a stock response deployment in API Gateway. API Gateway will serve the API. It will return the example response for clients invoking that API. This is also useful to be able to test that API to validate that it is meeting the requirements for the project. Once the backend web service is implemented, then that can be connected in API Gateway to serve the ultimate request. So to create and prototype an API, you create an open API description, and you can use any tool that you wish. You can load this into your API Gateway. Then you can deploy the API, and API Gateway will automatically define it as a stock response and use your example in your open API description. Then you can test it out with your client. Let's go into API Gateway. We'll build an API description, load it into API Gateway, deploy it as a stock response, and test it out. Here we are in the OCI console. We'll navigate over to API Gateway under Developer Services, API Management, and we'll choose APIs. APIs represent a repository of API descriptions. I'm going to go into an existing compartment, and we can see some that we already have loaded. We can support both OpenAPI 2.0 and OpenAPI 3.0 definitions. So this is an example of one such definition that we have loaded. What I'm going to do is go ahead and work on one of these APIs or show how we might be able to edit one of these APIs. Very simple. There's many tools on the market. One such tool is Swagger Editor. I pulled this up in my web browser, and I have an API definition. What you can see here is this is a field service API. It's a sample ticketing system. So in this API, we have a definition of services, such as to get tickets. It includes information about the required parameters for the service. It also includes some example data that can be used for generating samples. So what we're going to do is we're going to deploy this or load this into API Gateway. So within API Gateway, I'm going to choose my compartment that I want to work with. And I'll work with my L100 compartment. I'll go to my development compartment. So what I'm going to do is I'm going to go ahead and create an API, and I'll call this field service. And what I'm going to do is I'm going to choose my file. So here's a copy of my API description. This was written with a file name of swagger.yaml. Swagger is old name that we used to call OpenAPI definitions. There's still Swagger tools that we work with, and that's what Swagger now stands for today, is Swagger tools. OpenAPI is the new term. So if it's OpenAPI 2.0, that's what was formerly called Swagger. And if it's OpenAPI 3.0, that's the next format of OpenAPI. API Gateway does support both. In this particular file, I have OpenAPI 2.0. So I've loaded this into API Gateway, and a couple things are happening. One is the API Gateway is validating the file that I've loaded to make sure that it is semantically correct. And then what it will do is it will create a predefined deployment object that can be used to quickly create API definitions for this API. So it's validated, and now the deployment specification is generated. So I'll go ahead and deploy this to a gateway. So I can choose deploy, and I can go ahead and choose my gateway. And this is my L100 training gateway that I created, so I'll use that. I'll call this field service, and I'll give this a path prefix. So I'll just call this FSV1. I can call it whatever I want. Now, what I have here is a number of policies. So we'll get into detail with the different policies that we're going to be using. But what I'm going to do is I'm going to go ahead and add one necessary rule for a test client that I'm going to use in a moment, and I'll explain that shortly. So what I'm going to do is I'm going to go ahead and say I want to allow all origins, I want to allow all methods, and I'm going to allow loud header of x-api-key. This is a header that is included with that API definition, so I'm including that. This is to make a test client work that I'm going to use. There's many different test clients, many different ways, and I'll explain that as we go through. I'm going to go ahead and apply that change. I'm going to go to my next screen. What we can see here is there's a stock response that's automatically pre-populated for us. This was the example that was within that definition. So when I load this into API Gateway, it automatically creates or pre-populates my route for me. This is the method that I had defined, which is just a get. And of course, this is a stock response. This can go against Oracle functions, or it can also go against HTTP backends. So I'm going to go ahead and create my API. This will take roughly about 30 seconds on average, 30 seconds or less to go ahead and create the deployment, and we'll go ahead and test it. So in this case, what I'm going to do is I'm going to copy the deployment, and I'm going to go into my test client while it's deploying. So I can come back here to Swagger Editor. There's two elements here that I've left not populated, and I'll go ahead and start populating these. So I'm just going to paste the endpoint that I have and go ahead and make some changes. So here we have the host value, and then we have the base path value, which I'll go ahead and take these, and I'll put these in place in my file, and I'll go ahead and uncomment these. Take out the to-do, and I'll also take out the to-do here, the base path. Okay, so I have this created. This is set. And so what I can see here is in Swagger Editor, I have my code or my Swagger file, which is written in YAML. It can also be written in JSON. And then I have on the right-hand side dynamically generated documentation. That includes a tester. So what I can do is go ahead and select this, and I'm just going to give this a API key. I'm not doing anything with the API key right now. I'm just using it to satisfy the request. So what we see here is I've made a request. So it's called the service, and I've gotten a response. Now there's no backend service implemented. It's just within the gateway. And the gateway is returning a response. So what I can do is work with my team, and I can work with my front-end developers and my back-end developers, and we can make sure that this API definition is doing what we want. And as long as we're all comfortable with what's happening and the kind of behavior, then what we can do is send the front-end developer teams off to go build the front-end apps. The back-end developer teams can work on the back-end developer apps, and then they can go ahead and tie the API gateway to the actual backend when they implement it. But just for an example, I'm going to go ahead and copy the syntax here, and we'll go ahead and open up a terminal window. And if I were to paste this, what we should see, of course, is a return. Make this a little bit nicer. Let me see if I can get this as well. I'll just go ahead and paste this. There you go. So I get that nice formatted that we can see here the response. So this is a live service. We can go ahead and call this, start writing front-end applications and work against the API. Now, this is one tool that I've shown, Swagger Editor. You can use multiple tools. So like, for example, we can go on the Stoplight. We have the service here that we're working within. It's the same thing. All we're doing is just taking the file, the Swagger file or the OpenAPI definition, and we're just loading it into our OCI API gateway. Another example, just to call out real quick, to kind of show how open everything is and how you can use different tools, is we can go ahead and take this endpoint here, and we could go over to another popular tool called Postman. So here I'm in Postman. And so what I can go ahead and do is create a new request. I can go ahead and call the request here. Now, what you'll notice is I'm not really doing anything with that API key. I'm not validating that API key yet. This is just a stock response that's giving me that response. So with this, I've created an API description. I've loaded that API description, API gateway, and I've gone ahead and created a deployment of my stock response and tested it within my test clients. And so that's the demo.
Excellent work on completing module. That was a lot of information to learn. Congratulations. In addition to covering the basics of a microservices architecture as well as containerization concepts, the goal was for you to become familiar with the high-level architecture concepts and use cases for some important OCI developer services to include container registry, OKE, Oracle functions, API gateway, as well as learning about the DevOps service. Make sure you review those skill check questions, and then it's time to move on to the next module, Deliver Infrastructure as Code. Keep enjoying your journey.
Welcome back. In the last few videos, we discussed configuring our resources using Ansible. Now, we're going to turn our attention to managing what resources are even provisioned using Terraform. Terraform is composed of two main parts. The first is a declarative language that lets you codify infrastructure stacks. Don't worry about the details quite yet, but here we can see a portion of Terraform code that declares a compute instance in OCI. The second main part of Terraform is an engine that uses Terraform configurations to create a plan for making real-world infrastructure look like what is specified in the code. Again, don't worry about the details, but for example, if we give Terraform the config from before, it generates this plan to create a compute instance. It can then take this plan and convert it into API calls to any infrastructure provider. This includes not only IaaS like OCI, but also PaaS like Kubernetes and custom on-premise solutions. When using Terraform, we can think of infrastructure management in 3 parts: initial provisioning, maintenance and evolution, and eventual decommissioning. At the start, you write your Terraform code, feed it to the Terraform engine, and it provisions the infrastructure. Then, as your needs change over time, you can modify the Terraform code, and the Terraform engine will compare it to the existing infrastructure to then reconcile the two. Once it comes time to decommission the environment, one command allows Terraform to clean up all of the resources that it's provisioned. This workflow is what infrastructure as code is all about, and it has myriad advantages. You can reproduce stacks across environments, parameterize and version control infrastructure, create reusable hardware modules, and basically get all of the tools and techniques currently available for software development for hardware. Easing into the details, Terraform does this through a very simple CLI. There are 3 main commands that you'll ever need to execute: plan, apply, and destroy. We're already kind of familiar with Terraform apply. It takes a configuration file and provisions the infrastructure. However, it also writes a file called the state that represents Terraform's view of the world. After thinking about this for a while, you might ask, what about if the infrastructure changes without Terraform? Perhaps someone logs into the OCI console and provisions a new machine. For this, Terraform has an action called refresh that looks at the real-world infrastructure and refreshes the state file based on it. By default, this command is implicitly executed before any of the core actions, but in more complex implementations, it might be turned off. Before you run apply, however, it's best to run a Terraform plan. This compares the configuration to the state and generates a plan for getting the state to match the configuration, often called a diff. You can look at the diff to confirm that your Terraform code does what you think it will. By default, Terraform apply runs a Terraform plan and asks for your confirmation. But again, in more complex implementations, this might be turned off, and Terraform apply will require an explicit Terraform plan. The last command is Terraform destroy, which, as the name suggests, destroys all of the infrastructure that was under Terraform's purview. Before we get too much into the weeds, let's go through a quick example of using Terraform to provision a VCN and a compute instance. First, we'll head over to VCNs. We'll click the menu, Networking, Virtual Cloud Networks, and select our compartment. We can see that there's nothing here, so let's take a look at some Terraform code that will add a VCN with one subnet. Don't get caught up in any of the syntax just yet, we'll discuss that later. All we want to note is that we have one block that configures a VCN named Terraform VCN, and one block that configures a subnet named Example Subnet. We can head to the terminal and run Terraform plan. You can see that it outputs a list of changes that it'll make. Now let's go ahead and run Terraform apply. It outputs the same list of changes and asks us whether we want to proceed. We'll say yes, and it'll go ahead and start creating the networking resources. Now, if we head back over to the OCI console, we can see that we have our VCN. We'll click on its details. And it has that subnet. Now, let's see if we can modify the Terraform code to include a compute instance. First, let's navigate to compute instances just to see what I have. We can see that I just have a terminated instance from a test I ran earlier. Now let's head back over to the Terraform code, where I've added 2 blocks. The first one just selects an availability domain, but the second one configures an instance in the network we just provisioned. Now, if we run Terraform apply, it creates a plan, prompts us as before, and goes ahead with creating the instance. You might want to take a second and stand up and stretch your legs here. Okay, it's done. And we can see that the console now shows our new instance in the running state. To wrap up, let's run Terraform destroy. It'll ask for confirmation, and it'll destroy the subnet, the compute instance, and the VCN. Now that it's done, it'll show the instance is terminated, and the VCN that we created will be gone. So that wraps up our intro to Terraform. In the next video, we'll talk about how it integrates with different platforms, and we'll dig a little bit deeper into the language. See you there. Welcome back. In the last few videos, we introduced writing Terraform configurations and using them with the Terraform CLI. In this video, we'll discuss how we can improve that workflow with OCI Resource Manager. In our first model for Terraform, you draft configurations on your local machine, run Terraform on your local machine, and it reaches out to cloud providers like OCI to manage infrastructure. It's great for experimenting, but there are 2 obvious problems with this approach. The first is lack of version control. You need to keep track of various versions of the code for things like rolling back and branching for features. The second is in collaboration. You have to centralize the configurations and plan outputs to make sure everyone is on the same page. This leads us to storing the configuration and plan outputs in a centralized version control repo. So now we have this model where everyone can collaborate. Note, the state isn't uploaded because it can contain sensitive info like OCIDs and IPs. Contributors then write configs and test plans on their local machines before merging changes together. One pulls from the latest version in the shared repo before running apply. Okay, this is a great improvement, but there are still a couple problems. To understand those problems, we need a quick tangent on Terraform apply, plan, and refresh. When you call apply, it calls plan, which calls refresh, to update the state, which is used to generate a diff, which is executed to provision the infrastructure. The flow for plan is the same, except the diff isn't executed. This works well for small stacks, but for larger, more complex ones, refresh becomes an expensive operation, especially because it relies on API calls to the infrastructure. Similarly, actually computing plan becomes very expensive on more complicated stacks. To deal with these problems, we get rid of the automatically cascading invocations and replace them with manual invocations. Almost. Technically, explicit invocation of refresh is deprecated and is done with an option when calling plan. Okay, now that we have a more sophisticated workflow, what does that get us? Let's look at the diagram again. First, the state file isn't centralized, so different configuration authors could be working with different state files while calling test plans. Second, the actual diff that is executed against the infrastructure isn't centralized, so there's no guarantee that what happens is what everyone agreed on. These bring us to our third model for Terraform usage. If we actually run Terraform from within the cloud, we can guarantee that we're using the latest version of state or diff files. In this workflow, we draft configurations locally, sync them with a centralized repository, and execute plans and applies in a centralized manner. This brings us to a really important tool to get familiar with, OCI Resource Manager. You can think of it as a cloud-based Terraform host for centralized source control, state management, and job queuing, plus some Terraform-based automation like resource discovery and drift detection. We'll go over each of those in detail later, but for now, let's dive into this workflow with a demo. To start, we have Terraform in a GitHub repo. Let's look at the main.tf file. It configures Terraform, then it configures the OCI provider, and this code provisions a VCN and 2 subnets within it. Now let's go to the variables file. Here, we only have 2 variables, compartment ID and region. The next step is to create what's called a stack in Resource Manager. A stack is a set of resources to manage infrastructure. For our demo, we'll mirror our GitHub repo. We'll start at the homepage of the OCI console. Navigate to the menu, Developer Services, and Resource Manager. Here, we can select stacks, and let's go ahead and create one. You can upload Terraform configuration files directly, use an OCI provided template, mirror from GitHub or GitLab, or create one based on an existing compartment. We'll mirror from GitHub. Here, you select configuration source provider, which is just a connection to GitHub or GitLab with an authentication token. I'll select the connection I made to GitHub earlier. I'll select the repository I just showed, and I'll select the main branch. Here, we can name the stack. Select its compartment, Terraform version, and let's go to the variables. Right now, this part just reads the variables file and provides us fields for each variable. We'll grab a compartment ID and select Phoenix for the region. We can review, and let's create. Now we've created a stack, but we haven't run any Terraform. For that, we'll have to hit the plan or apply buttons. So now we have a stack with a configuration, and since we selected to not provision immediately, we also have a state file that just states that nothing is provisioned. We can also hide the local machine and GitLab from the picture for now. Next, we want to run a plan. For every stack, there's a queue of jobs, commands that will be run. We'll add a plan to the job queue, which will lock the state file, get passed to the Terraform host, which executes it and generates a diff. Once that's done, the state file will unlock. Let's go ahead and hit plan now. Let's name our plan. And hit go. It'll take a second to run, but here you can download the Terraform configuration, as well as cancel the job. You can view all of its details here, and it'll show all of its outputs down here. So you can see that it finished, and it created the plan down here. Finally, we'll add an apply to the queue that will lock the state file and execute the diff to provision the infrastructure. We're going to go ahead and hit apply, name the job, and then we can choose either using an existing plan or running a new one. We'll choose an existing one, and we'll hit go. And you can see that it succeeded, and the logs are down here. Now let's go back over to the VCNs to see what it created. You can see it created the example VCN, and it should have 2 subnets. So that's the basics of using Resource Manager for Terraform. In the next video, we'll go over how to handle when infrastructure and Resource Manager are out of sync. See you there. In the last video, we went over a basic overview of the Terraform workflow. In this video, we'll talk about what you need to know to get started writing Terraform configurations. In order for Terraform to do anything, it has a key concept called providers. Recall that we have this model of Terraform being all about the interplay between configuration, state, and diff, and the real-world infrastructure. And, as mentioned before, Terraform can manage infrastructure across multiple platforms, including custom ones. But this brings up the question, how can Terraform actually be platform agnostic? To figure that out, we have to take a closer look at the internals of the Terraform engine. There are 2 main parts of the engine, the Terraform core and plugins called providers. The core figures out everything in a platform agnostic way. Then, the providers translate that into the platform's language. To be a little more specific, providers are Go language executables that translate between Terraform's diff, refresh, and apply functions and the target platform's CRUD API. HashiCorp maintains a registry of official, verified, and community providers that you can install. The official ones will install automatically if they're specified in the Terraform configuration. Okay, now we can get into the real meat and potatoes of Terraform, the language itself. The big thing to know is that Terraform is declarative. That means that, for the most part, it consists only of blocks that declare resources, labels for those resources, and parameters that configure that resource. To get a sense of the language, let's read over a very simple example together. First, we have a block that configures Terraform itself. In that block, we have another block that lists the providers that are used. In this example, we only listed OCI, but we could specify more as needed here. Next, we have one configuration block for each provider, in this case, one for OCI. Any of the official or verified providers will have docs on the Terraform registry for what arguments are needed. So here, we can see that we chose a region, method of authorization, and a user profile. Finally, we have a resource block. This one declares that we have a VCN named example. When you write these, you basically search the docs for the resource you want to create and fill in the attributes that it asks for. In this example, we fill in a DNS label, a CIDR block, a compartment OCID, and a display name. If we wanted to improve this configuration, we would first notice that we have some hard-coded values, like region and compartment OCID. We can factor these out by declaring them as variables and defining them all together. This way, we can parameterize the Terraform configuration to be reusable in many different forms. So if you look at this example Terraform code available on GitHub, you can see that they wrote it using a bunch of variables. A couple interesting ones include num instances, where you can change the amount of instances that you provision with just a number, and changing the instance shape, as well as the OCPUs and the memory. These kinds of variables are very useful in creating configurable, reusable chunks of code. To improve our code even further, Terraform has a concept of code reuse called modules. To illustrate that, suppose we have a Terraform configuration for a VCN and related resources. You could then use that VCN configuration as what's called a module and embed it inside of another configuration. So in this example, we're calling the VCN module twice to provision it twice. This way, you could reuse the VCN module in different configurations to construct a hub-and-spoke network topology, for example. You could then use the hub-and-spoke configuration as a module in an even larger application, and so on. HashiCorp maintains a registry of modules and examples. In practice, when writing Terraform, you want to use these as much as possible. Admittedly, Terraform goes way deeper than is within the scope of this course. For that, HashiCorp maintains very well-done tutorials and documentation that I highly recommend perusing. For this course, like with Ansible, we're only looking to get a sense of the workflow, so that when you decide you want to implement infrastructure automation, you know where to start. So that's all we have for general Terraform knowledge. In the next video, we'll talk about the tools available in OCI to facilitate Terraform usage. Welcome back. In the previous lesson, we introduced Resource Manager to provision and manage infrastructure. However, we assumed a perfectly linear workflow where all changes made to the infrastructure are made through Terraform, which is not totally realistic. To mimic this, I made two changes to the VCN. First, I added a new subnet. Second, I added another CIDR block. This is called drift, the process of real infrastructure slowly diverging from what was configured. For this, Resource Manager can run what's called drift detection to compare the configuration and the infrastructure to generate detailed drift reports for each resource. To do this, we'll go to our stack in the console and click More Actions, run drift detection, and confirm. We now have a drift detection work request down here. It'll take about a minute to run. Now that it's done, we can go back to More Actions, view drift detection report, and we'll see that it's detected a modification on the VCN, specifically a new CIDR block. We'll minimize those. And we'll see that while it did detect the new CIDR block, it didn't detect the extra subnet. This is because drift detection only reports on resources that Terraform knew about already. We can address this, but to do that, we'll take a quick tangent. Another problem with our idealized workflow is that it's not realistic to always draft the Terraform first and then provision a stack for it. Sometimes it's easier to just mess around in the console and provision the infrastructure first. For this, Resource Manager can take all of the infrastructure in a compartment and generate the stack and configuration based on it. To do this, we'll go to our stacks and create a new one. We'll select existing compartment, pick the compartment we want to scan, and select the services that we care about. In this case, core services. We'll name our stack, and go ahead and create it. It'll take about a minute to run. And now we have a stack based on the existing resources in a compartment. You can download the Terraform configuration right here. If we open up the Terraform, we can now see how we can address that extra subnet that drift detection didn't catch. We can take the Terraform from here, paste it into our Terraform configuration, and update the state using Terraform CLI. We can also update the VCN's Terraform with the new CIDR block captured here. Now, we can not only use Terraform and Resource Manager to provision infrastructure, but we can also use drift detection to find changes and resource discovery to write Terraform for us. This way, we can support a more non-linear workflow that's representative of the real world. In the next video, we'll talk about extending the console to support our stacks more seamlessly. See you there. In the last few videos, we talked about using Terraform with Resource Manager. Now, we'll discuss some final touches streamlining Terraform usage with OCI. So far, we've talked about using Terraform as an input to Resource Manager to provision the infrastructure, as well as using Resource Manager to write Terraform based on existing infrastructure. This picture should be a little more complex though, because we'll often use the same configuration to provision multiple stacks. For example, we might have a development, QA, and a production environment. Also, in a microservices-based application, as we'll talk about in later modules, an application can be broken up into multiple loosely coupled pieces. Finally, one of the big parts of DevOps is that it's not only traditional ops people that manage infrastructure, but also traditional developers that aren't necessarily experts on Terraform. The way Resource Manager makes it easy for DevOps personnel to manage infrastructure is by allowing you to hide the Terraform away into what are called templates. To make a template, we can just upload our Terraform configuration here. It'll also need a schema document, but we'll address that later in this video. To use a template, we'll go to the stack creation form and select to use a template. Here, we can select between Oracle provided templates and our custom ones. Then we just need to go through and fill in all the variables. A template consists of two pieces, a Terraform configuration and a schema document. You should be familiar with Terraform configurations, but schema documents are probably new. These are YAML documents that list the variables in the code, the constraints on those variables, and what variables to show on the stacks page in the web console. These allow the web console to render forms for provisioning these stacks. Let's run through an overview of the syntax before showing an example. The fundamental thing that is specified in the schema document is a list of all of the variables. In this example, we specify a variable named functions app name that takes a string. The field is titled application name and has the description do not use spaces. It ends up getting rendered like this. The other main thing that is specified is how variables are grouped. To specify a variable group, we just give it a title and a list of variable names. Each variable group renders as a box of fields to fill in. For this example, let's walk through some simple Terraform. The first block configures Terraform. The second block configures the OCI provider. The third configures a VCN. The fourth configures a subnet in that VCN. And the fifth declares a compute instance in that subnet. Note how we factored all the parameters out into variables. Now let's take a look at the variables file. Here, we declare everything, but we skipped specifying anything about the variables because we'll do that in the schema document. If you intend on also using the Terraform CLI with these configurations, you should fill this in too. Onto the schema document. The first block gives the template a title, description, and quick blurb. This is displayed when selecting between templates. You could also add a thumbnail here, but it's optional. The next main block that we have is for variable grouping. Here, we have a group for hidden, auto-populated variables, in this case just region. And then we have a block each for the VCN variables, the subnet variables, and the compute variables. The VCN variables just include the compartment, the display name, the DNS label, and the CIDR block. The subnet has the same variables, just with different names. The compute has compartment OCID, display name, shape, image, and availability domain. Here's where we actually specify the metadata on each variable. First, let's look at region. Type is the most important thing to specify. The OCI docs have a list of allowed types. By specifying that it's a region, OCI can then just auto-populate this variable. Next, we give it a title and say it's required. Now, let's look at the VCN variables. By giving compartment ID its respective type, it tells OCI to provide a dropdown of all the available compartments. This way, you don't have to go searching for OCIDs anymore. Then, we just say it's required and give it a title and description. String-based variables like display name are largely boilerplate. However, some string-based variables, like CIDR block, are best given a regex pattern for input validation. For DNS label, we give it a maximum character length of 15. The subnet variables are identical, so we'll skip that. On to compute variables. Compartment ID has the same configuration as before. Display name is also very straightforward. Shape is more interesting because by specifying its respective type, OCI will give us a dropdown of possible shapes. By saying it depends on the compartment ID, it will also filter by the shapes that are available in the selected compartment. Likewise, for image, it gives us a dropdown that we can filter by the compartment and by the compute shape chosen above. Finally, for the availability domain, it can get us a dropdown with the AD names that are specific to our tenancy. Now, we can take a look at how this renders when provisioning the stack. We'll start off by hitting Create Stack. Then we'll upload our configuration. This is the one that I just showed. Here's where it shows the title, info, and thumbnail. We'll name our stack. And we'll see that the description was pre-populated. Now here's where the schema document does all the heavy lifting. We'll use this dropdown to choose our compartment. We'll name the VCN. Give it a DNS label. And give it a CIDR block. Now we can do the same for the subnet. We'll select our compute instances compartment. Give it a name. And now notice how compute shape fills in with the default, and the dropdown is populated by available shapes in the compartment. The dropdown for image, then, is filtered by compartment and by compute shape. Finally, we'll pick our availability domain. Now let's create the stack. And we'll hit apply. This will take a few minutes to run, but I'll cut that. Now that it's done, we'll go ahead and look at our resources. Go to the menu, networking, virtual cloud networks, and we'll see our VCN. Now let's go back to the menu, hit compute, instances, and we'll see our example instance. And that wraps up our module on infrastructure automation. We first went over configuration management with Ansible and demonstrated how to configure multiple machines with Ansible plays and playbooks. Then we gave a brief introduction to infrastructure as code with Terraform and using it with Resource Manager. Then we went over detecting changes with drift detection and using resource discovery to write Terraform for us. Finally, we went over using templates and schema documents to neatly package a Terraform configuration for easy reuse. We went over a lot, and all of this stuff goes pretty deep. But what's important is that you should have a feel for managing infrastructure in this way and would be able to dive deeper on your own when needed. For the certification, I highly recommend that you write some Terraform and play with it in Resource Manager. You can do a lot with just the free tier. With infrastructure automation in our toolbelt, we can start to think about the application that sits on top of it. How can we structure the software in such a way that's conducive to the fast-paced DevOps lifecycle? For that, I'll pass the floor to my colleague Mahendra Mehra to dive into microservices and orchestration. See you there.